Hello everyone. In this section we will try to understand how do we come up with the width and height of core and die. Okay, so in the physical design overview flow, this was the first step to define the width and height of core and the die. That was the first step of the physical design flow. So in this sections, let us try to understand how do we come up with the values of W and H. Okay. So what we'll do is we'll start with the basic netlist, and the basic netlist that we'll be using is, let's say, two flip-flops, the launch flop and the capture flop, and you have a simple combinational logic in between them. Okay, so our netlist will be considering only of this one for now. Let's say if we are trying to get the width and height of core and die, so let's take this as an example to identify the width and height of the core and die, and then this can be extrapolated to millions of gates. Okay, so this is the netlist, basic netlist that we have, and some connectivity. So A1 and O1 are your AND gates, OR gates, and they are basically they fall under the class of standard cells. And the flip-flop 1 and flip-flop 2, they fall under the class of registers or flip-flops. Okay, so this is the netlist. A netlist basically defines the connectivity between all the components. Let's move on. So in this case, we are mostly while defining the dimensions of the chip, we are mostly dependent on the dimensions of the logic gates which is sitting over here. So basically we are dependent on the logic gates and dimension of the AND gate and the OR gate and this particular flip-flops. So let's try to give a proper length and breadth to this particular gates, and this is how it will look like. So you have your launch flop with a square shape or a rectangle shape. You have your AND gate with again a rectangle shape. You have the OR gate and you have the flip-flop. Okay, next step, what we are mostly interested is to find out the dimensions of your core and die. So in that case, we are mostly interested in the dimensions of the standard cells and not the wires as of now. The wires will still play an important role in the further steps, but in this case where we want to identify the dimensions of the chip, we are mostly interested in the dimensions of the standard cells. So let's try to give a rough dimensions to all of them. Let's say the standard cells are given a dimension of 1 unit by 1 unit. This is 1 unit and this is 1 unit. So the area of this particular standard cells, all of them, will be 1 square unit. So this is 1 square unit, this is 1 square unit. And also let us assume the same area for the flip-flops as well. Okay, so the area of the flip-flop will be 1 square unit. Okay, so now what we'll do is, with the help of this netlist, with the help of these dimensions, we'll try to identify the area which is occupied on the silicon wafer. Okay, so but before that, let's try to place we'll remove the wires, and let's try to club all of them in a single plate. So for example, we'll bring the flops over here, we'll bring the AND gates and the OR gates all over here. And now if you try to calculate the total area or total length and width, so the length will be 2 square units, the width will be 2 square units, and the overall area is 4 square units. Sorry, the length will be 2 units, the breadth will be 2 units, and the area will be 2 into 2, which is 4 square unit. Okay, so now we have a rough dimension, or we have a rough calculation of the area of the netlist. So this is the area of the netlist, area occupied by the netlist, minimum area that will be occupied by the netlist wherever it is placed. Okay, let's look into the core and die of section of a chip. So for example, this is your silicon wafer on which you implement all of your logic. This section is the section which is this one section is referred to as your die, Okay, and inside the die you have this core. So this is the core section where you place the fundamental logic, where you actually place this logic, and this is the die section. Basically this encapsulates your core. Okay, and this is the piece of the area on which your circuit is built. So your circuit will not exceed this area. That's what the point is. And we imprint this particular die multiple times on the silicon wafer to increase its throughput. Okay, so those are all the fabrication concepts. Let's come back to defining the width and height of core and die. So let's try to place this particular logic inside the core and see what happens. So if you see, this particular netlist, which was of 4 square units, occupies the complete area inside the core. So what does that mean? You have actually utilized your core 100%. Okay, so if there was some area left out, then it would not have been 100%, it would have been some other percent. But in this case, your complete logic, your netlist is completely occupying the core area, and that's why we call it as 100% utilization. And your utilization factor, so with the help of the 100% utilization, we come up with a term which is utilization factor, and the definition for utilization factor is the area occupied by the netlist, which is 4 square unit, divided by total area of the core. So area occupied by the netlist is this particular netlist, and total area of the core is the area of this particular core. So if we put in the dimensions over here, the area occupied by the netlist is 4 into 1 square unit. Okay, and the utilization and the total area of the core is 2 into 2 square units, so which is 4 square unit by 4 square unit, and the utilization factor comes to 1. So when we say the utilization factor is 1, which means your core is completely occupied, and if there are some extra cells that we need to add in the core, that is not allowed, or that is not possible, because there is no space left. So in a practical scenario, we ideally have some amount of, we don't go for 100% utilization, we go for a 50-60% utilization, and the utilization factor will be 0.5 or 0.6. But for the proof of concept, we are trying to explain that 100% utilization means your core is completely utilized, and there is no space to add any extra logic. Okay, with this particular, let's try to explain one more concept with the same example. You have this aspect ratio, you have the concept of aspect ratio. So when you say the term aspect ratio, or the definition of aspect ratio, is height by width. So in this case, the height of this particular logic is of this particular core is 2 unit, the width is 2 unit, so the aspect ratio comes to be 1. So whenever the aspect ratio is 1, it signifies that the chip is a square shaped. Whenever your aspect ratio is some 0.5 or something, or some other number other than 1, it signifies it signifies that your chip is basically a rectangle shape. Okay, so what we'll do is we'll take some more examples. Let's say we'll take another example, and we'll keep these definitions at the right side. The utilization factor is area occupied by the netlist divided by total area of the core. Okay, and the aspect ratio is height by width. Okay, with that in mind, let's take another example. So we have the same netlist with 2 unit as the length and 2 unit as the height, and let's say now the area, now the core and the die look something like this. So this is your core, And let's see the dimensions of the core. So the core is 2 unit height, the height of the core is 2 unit, the width of the core is 4 unit. Okay, in this case, and now we place this particular logic inside this. So if you place this particular logic inside this and go by the definition of utilization factor, in this case the numbers will look something like this. So utilization factor will be 2 square, the area of the netlist, which is 2 unit cross 2 unit, and the total area divided by total area of the core, which is 4 cross 2. So this is 4 cross 2. So utilization factor will come to across 4 square unit by 8 square unit. So utilization factor is 0.5. So 0.5 signifies a rectangle shape, or anything other than 1 represents a rectangle shape, or anything other than 1 represents that you have the core is 50% utilized, and the remaining there is some extra amount of area that can be used to place some additional cells. For example, you need some optimization that has to be done. You can use this area to add some buffers or something. Okay, and similarly, if we try to calculate the aspect ratio for this particular dimension, it will be 2 by 4. So this is 2 divided by 4, which is again 0.5. So you must have heard these terms, aspect ratio and utilization factor, while building a chip or while doing a floor planning. So this is what it actually means, and this is how it comes from. So what we'll do is, since we'll take some more examples, let us take an example of a square chip. So since I'm already running out of time, let's try to take an example of a bigger chip. We'll try to place this logic inside this and calculate the utilization factor and the aspect ratio. Let's try to do all this in the next video. Thank you.